I want to tell you a story about the way we build technology. And I want to tell you a story about the way we're going to build technology in the future. A future that will be defined by the development of quantum technology, quantum tech. The realization of quantum technology built from the bottom up, atom by atom, electron by electron, represents one of the most profound transformations in the way humanity builds things in history. Because if we look back, we see that the way we build technology has barely changed over millennia. We'll start with a large piece of precursor material, like brass, and we'll gradually whittle it away to a target technology through something known as top-down fabrication. And we can get a gear at the end. This is very powerful. This has given us the Industrial Revolution. But it's also set us on a stage to today's information age. In 1837, Charles Babbage developed this system, the analytical engine. This is the world's first general-purpose computer. It's a computer that processes information using mechanical devices, gears, pulleys, levers, like I showed you just a moment ago. Now, this particular system was never finished, and parts of it actually reside at the University of Sydney. But it was the first major step to today's information age. More than 100 years later, we saw another major transformation with the development of this system, ENIAC. This is the world's first electronic computer. This is a computer that processed information by controlling the flow of electricity. It was the absolute pinnacle of technology in the day. It took an entire room filled with racks, cabinets, connectors, plugs, and these things, vacuum tubes. These are the fundamental electrical switching elements that allow us to control the flow of electricity with another electrical signal. These are what allowed us, at the time, to perform computations using electricity. But they're big. They're about the size of your fist. Just a short while later, we saw another major development that allowed us to fabricate wires alongside a new kind of switching element, transistors, forming complete electrical circuits on a single chip and at a dramatically reduced scale. These are integrated circuits. Fast forward to today, and integrated circuit technology allows us to build literally over 1 billion of these active switching elements on a chip no bigger than your thumbnail. This is what powers the information age. Microprocessors are literally everywhere, embedded in all the technology around us. This has changed the world. But as remarkable as this is, if we take a step back and take a deep breath and look with a critical eye, we see that the way we built technology, going from brass to a gear, is actually still in play. In this case, we start with a large piece of precursor material called a silicon ingot. We slice it to form a wafer, and then we pattern the surface to build the technology we want. For instance, a microprocessor. And this patterning is very similar to the way you might machine the teeth of a gear. These are both top-down fabrication. But building on research begun in the late 1970s and early 1980s, we now stand at the precipice of a radical change in the way we build technology. Instead of starting from the top and working our way down, we're now looking to build technology from the bottom up, atom by atom, electron by electron. This is a picture of one atom of ytterbium from my laboratory. We can confine it in space using a special electromagnetic bottle called an ion trap. We can manipulate it using laser beams and microwaves. We can take a picture using a camera that's not dissimilar from the one in your phone. We can trap one, or we can trap a few. And because these atoms are charged, they form neatly ordered arrays, crystals. This is matter synthesized from the bottom up, atom by atom. And these individual atoms form the building blocks of a new generation of technologies that get their power not just because they're smaller or more compact, but because on these scales, the familiar laws of nature give way to the strange rules of quantum physics. Nature on these scales ceases to be absolute. The picture that many of us have in mind of quantum particles like atoms or electrons as billiard balls that bounce off each other or off the walls has to be replaced by a picture in which we conceive them more like waves. Waves that spread out in space. waves that interfere with each other, or even with themselves. Nature on these scales even appears to possess its own form of magic. Entanglement allows particles obeying the rules of quantum mechanics to be linked together over vast distances, so manipulating one instantly affects its partner in ways we fundamentally don't understand today. These technologies that we're looking to build will be a radical departure from what we've done before. Today's technology completely glosses over all of this phenomenology. These phenomena were long derided by the greatest minds of the 20th century. Even Einstein referred to entanglement pejoratively as spooky action at a distance. These were things that were long relegated to the dustbin of mathematical curiosities, but no longer. These phenomena are real and accessible in the laboratory, laboratories like mine. And now we're learning how we can control and harness these phenomena as resources powering a new generation of technologies, much the way we use the flow of electricity to power our technology today. For an example of the kind of technology we're trying to build, consider quantum simulation, a topic my group works on. We take inspiration from the development of modern aviation, where for decades, engineers would build scale models of aircraft and study their behavior in wind tunnels. We're now working to build quantum scale models from the bottom up, atom by atom, electron by electron, to tackle challenging problems in material science and chemistry that could have truly profound consequences if we succeed. This is a picture of a quantum simulator that my team has worked on in collaboration with NIST in the United States. It's composed of about 300 atoms of beryllium. Each blue dot that you see is one atom in this photograph. Using the rules of quantum physics, if we were to encode a bit of information, a 0 or a 1, on each of these atoms, and this is something we can do routinely, then with 300 atoms, we could simultaneously represent 2 to the 300 possible combinations of how all those zeros and ones take their value. 2 to the 300 is about 10 to the 100, a googol, a number so astronomically large that if you tried to build a conventional supercomputer capable of simultaneously representing all of these combinations in memory, you would run out of matter in the universe before you succeeded. And here we achieve the same computational capacity using just 300 atoms of beryllium and the rules of quantum mechanics in a space less than a millimeter. To give you a flavor for the kinds of problems we're thinking about solving, let me tell you about the way electrons can interact in certain solids to give rise to exotic phenomena like superconductivity, through which electricity, current, can flow with no resistance, no loss. Despite many decades of research, one class of these materials with tremendous potential for application is very poorly understood. This is because the underlying physics comes from the way that electrons interact quantum mechanically. This is phenomenology that brings with it the same complexity of information representation that I told you about just a moment ago. These materials are extremely difficult to simulate on a computer. Can we imagine what would happen if we solved this problem? By building quantum simulators capable of representing a quantum scale model that allow us to crack these problems. Can we imagine the ability to transmit energy over huge distances with no loss? Energy loss in power distribution systems is a major challenge not only in grid design, but also in the uptake of clean energy. In fact, this is such a challenge that in the United States, which is known to have a very efficient power distribution grid, about 6% of energy is just lost sending it over wires. The wires heat up. Now, admittedly, 6% may not sound like much, but that 6% of energy lost is more than the total annual generation of electricity in Australia. Just lost in wires heating up. What would the world look like if we solved this problem? The modern information age has come about both because of the development of microprocessors, but also because of the development of capabilities allowing us to transmit data over vast distances with nearly no loss in fiber optics. This is the information superhighway, hopefully coming soon to Australia. Now, I don't want to get ahead of myself, But let's just imagine the profound social and economic changes that might come about if we could build an energy superhighway, allowing us to transfer energy anywhere in the world with nearly no loss. Quantum technology built from the bottom up, atom by atom, represents a radical departure in the way we build things. And the research we're doing in this space is very high risk. It fundamentally may not work. We may fail. And frankly, we don't even really understand what we might achieve if we're successful. In 1947, when the ENIAC was built, the world's first electronic computer, the team of engineers that originally developed it had only one application in mind: the calculation of artillery shell trajectories. And just look at how the development of electronic computers has completely changed the world, from finance to healthcare. History has shown us again and again that the most profound impacts of new technologies are those that are least anticipated. Building technology from the bottom up, atom by atom, electron by electron, has brought us to the brink of the quantum future. It's thrilling to me that Australia is leading the way in this field. So what will the quantum future look like? We'll have to wait and see. Thank you very much.